So hi, everyone. Welcome to our monthly Smart Water Software Solutions webinar series. My name is Sarah Milanig. I'm Associate Director at Colorado State University's One Water Solutions Institute, and I'll be the moderator today. Before we hand it over to Dr. Arabi, just a couple quick housekeeping items. This webinar is being recorded and we'll post it onto our YouTube channel. I'll drop the link for that into the chat so you can subscribe if you're interested. Participants are currently joined with your microphones muted and your cameras turned off, but I have the ability to activate those. So we can use the chat feature to track questions, but we'll also have ample time at the end of the presentation and demo to activate your microphone so you can speak directly with our presenter today, or you can raise your hand. Also, if you need proof of attendance for this webinar for the purposes of earning continuing education credits, you can shoot us an email at owsi@colostate.edu. I'll throw that in the chat as well, and we can provide confirmation of attendance. So today's webinar is going to dive into the key features of the CLASIC tool to explore real-world use cases and share some best practices to help you streamline your workflow. So without further ado, I'm pleased to introduce our presenter for today and turn this over to him. Dr. Mazdak Arabi is the Borland Chair of Water Resources and Professor of Civil and Environmental Engineering here at CSU, where he also serves as the Director of the One Water Solutions Institute. So Mazdak, I'll hand it over to you to get us kicked off.
Thank you, Sarah, and thank you everybody for joining us. It's very exciting to see this developing community for users of the CLASIC tool. Before I get into the details of the CLASIC tool, what I will do is first a little bit discuss the impetus for a lot of the tools and software packages that we develop at the One Water Solutions Institute, where we essentially focus on technological advancements and solutions that enable the One Water approach, and understanding some of the key issues related to the One Water is really important to understand the impetus for the CLASIC tool. And again, as I mentioned, a number of other tools that we have developed and we provide to users across the country and even internationally, and we provide technical support for people to use it. So as Sarah mentioned, as we go over the materials, both in terms of presentation and the demo, please feel free to ask questions at the end during the Q&A session by posting your questions in the chat or unmuting yourself to have a good dialogue about the CLASIC tool and other tools that we provide to support the One Water approach. The One Water approach essentially is an integrated planning and implementation approach where essentially there are three key components to the One Water paradigm. One is transitioning from an extractive model of taking water, using it, and then returning waste to a more circular economy, circular water type of systems. Also a paradigm where with integrate planning and management, different sectors that influence or use water coordinate and cooperate in managing water in a better fashion, and also thinking about future and resiliency of our water systems, and also issues of access to clean water for everybody, and also perhaps avoiding the water quality consequences of the way we manage our water systems are the key elements of the One Water approach as highlighted here. So there are many drivers to adopting One Water approaches. I see many folks here joining us from consulting firms and research institutions that focus on the One Water, so I trust everybody is familiar with these drivers. But these typically, the impetus for the One Water stems from aging infrastructure. We know that our water systems are aging, and benefiting from these systems and aging infrastructure to provide services to our communities is increasingly problematic. And then the aging infrastructure, not only they have to provide services based on the historical demands for the services, but also increased demands due to urbanization and population growth, ever increasing and stringent regulations with regard to water quantity and quality, and water institutions, obviously limited resources, and of course the reality of dealing with climatic extremes and climate change, both in terms of frequency and intensity, and also duration of extreme events, but also long-term changes in climatic factors and variables such as warmer temperatures and perhaps different precipitation regimes. Also, we are learning, or communities have learned, that water is embedded in almost every aspect of urban and regional planning and influences livability of our communities. And therefore, more and more communities are thinking about improving community livability in the way water systems are managed, and also shared prosperity that different economic sectors and social groups can benefit from our water systems. So we have conducted many studies, including this One Water rating system and assessment framework that we, in collaboration with the Water Research Foundation, we have put together. We have come up with 9 elements for the One Water approach, which encompasses institutional collaborations and governance, stakeholder engagement, water recycling and reuse obviously is a big part of One Water. But also you can see here factors that immediately influence stormwater, such as improving the resilience of water supply by harvesting stormwater and using that as additional alternative water supply for communities. Clearly, flood and stormwater resilience is a significant issue, not only in coastal communities, but also in many other communities inland that deal with increased frequency of very heavy precipitation and flooding and stormwater issues related to those, and watershed and ecosystem health in general. But again, as I mentioned, one of the core factors in the One Water paradigm is the integrated approach to urban planning and landscape architecture with water planning and management to improve community livability, quality of life, and affordability, climate resilience, and social, environmental, and economic justice issues that are well documented for this factor. So when we look at all of these factors, the ultimate goal or outcomes of the One Water approach, by reconciling these 9 key elements and objectives that relate to those 9 factors, the goals typically are to lower cost and improve efficiency of water systems, again, via coordination and collaboration, preparation or preparedness to climate change and climatic extremes, increased infrastructure resiliency and equitability, and obviously, again, improved environmental sustainability of the way we manage our community infrastructure systems, in addition to the siloed system-specific design criteria that we may have for our infrastructure systems. So if we look at, for example, flood and stormwater resilience, stormwater systems are very closely linked with land use activities. The way we conduct or use land in urban settings and in general in communities of different sizes clearly influences the stormwater responses in the community, and therefore development of stormwater systems, stormwater control measures, and stormwater planning must incorporate ecosystem health, livability, and resiliency outcomes to achieve improved outcomes for the community. So in this context, numerous stormwater infrastructure systems are considered, but perhaps the 3 primary categories of the systems include the traditional gray infrastructure systems that typically focus on collection and conveyance of stormwater in a community. But increasingly, we are looking at green infrastructure solutions, systems that are also referred to as nature-based solutions, where we try to mimic the natural hydrology of a region. And by doing that, we add to community livability as well as improved stormwater management capacity for the community. But also we are learning in many regions, particularly in the coastal regions, that some of these traditional and emerging nature-based solutions are not sufficient to handle mega storms with massive amount of precipitation occurring during a relatively short period of time. And the cloudburst type management systems are increasingly considered in these communities. That also is some of the systems that we consider in our planning processes. The CLASIC software was developed and is offered to various communities to support informed stormwater infrastructure decisions on the extent and combinations of green, gray, and cloudburst infrastructure systems. The CLASIC tool, although it can be used for scenario planning, is not intended to be a design tool or design system. It mostly focuses on planning and management and considerations with regard to lifecycle costs of infrastructure systems for planning purposes, and identifying solutions that can meet the goals of the community, perhaps at the lowest cost with the highest outcomes that can be obtained from these infrastructure systems. The project has been funded by numerous federal and local agencies. Primarily, it has been funded by the National Science Foundation and the Environmental Protection Agency in the United States. Also, many parts of the tool were developed in close collaboration with the Water Research Foundation to develop the tool in a way that is consistent with the needs and preferences of communities that are intended to use the tool. So in terms of scenario planning capacity of the tool, I break this down in 3 components. The first component of the tool is where land use change, population change, low impact development, and surface vegetation can be modeled in the tool. So even if we don't consider any stormwater interventions and control measures, one can simulate how stormwater conditions, both in terms of quantity and quality, will respond to changes in land use. For example, going from low intensity urban development to high intensity developed areas with higher imperviousness and factors such as again, imperviousness and density of development. Population growth can be modeled, and as I mentioned, there are specific places where low impact development can be handled. Also, CLASIC provides capacities for adding surface vegetation. Specifically, planting trees in communities is a big factor that many communities are considering. So adding trees to cities is a capacity of the system. With regard to climate, we have the capacity, or the tool has the capacity to assess the long-term changes in temperature, precipitation, and evaporation, and also changes in extreme precipitation regimes. These capacities are mostly provided by enabling the user to upload any user-specified climatic databases that they would like to consider for the area of analysis, and I will demonstrate those as we go over a live demo of the tool. And also, perhaps the most commonly used part of the tool is assessing the life cycle cost, triple bottom line, social, economic, and environmental characteristics, as well as hydrologic and water quality performance of gray infrastructure systems, green and nature-based solutions, and cloudburst systems for stormwater management. So the set of control measures that are available in the CLASIC tool are sand filters, infiltration trenches, storage tunnels and vaults, extended detention basins, disconnections, wet ponds, permeable pavements. So you can see many traditional gray systems for stormwater control, as well as green and nature-based solutions such as rain gardens, green roofs, grass swells. Stormwater harvesting is an item that is specifically available now in CLASIC. Stream restoration and cloudburst systems that require a little bit of understanding how to represent the systems in the tool. And as I mentioned, one may just simply consider trees in urban areas and how trees influence various triple bottom line factors that may be considered in the planning process. So here's an example of, for example, how we can add a rain garden in the CLASIC tool. So we have worked very closely with users and stakeholders in the water sector to understand how we can incorporate these stormwater control measures without making it too complicated for planning and management purposes. So for example, a rain garden may be added as a small unit, a medium size or a large size rain garden. Surface vegetation can be added, trees can be added, diverse surface vegetation or grass. Design parameters are available. So for example, one can add an under drain, liners and things like that, all of which influence not only hydrologic and water quality performance, but also life cycle costs and triple bottom line factors that are considered. And obviously maintenance can be included, recommended levels of maintenance, partial maintenance, or no maintenance at all. So in terms of the CLASIC, as I mentioned, has these four main categories of outputs and responses that it simulates. Hydrologic performance. So hydrologic performance typically refers to the hydrologic budgets, runoff, infiltration, and evaporation. Water quality performance. In the CLASIC tool, at this time, we only look at total suspended solids and nutrients, but we have created databases that in the next version of the tool, we will have capacity for many metals as well as E. coli that can be assessed in CLASIC. Life cycle costs, construction costs, operation management, and other type of costs, life cycle costs are included. And then triple bottom line co-benefits. All of these factors, a list of nearly 20 responses, then are available for analysis in a multi-criteria decision analysis tool to see what type of alternatives in terms of scenarios get these communities closest to their goals and targets at the lowest cost. So I'm highlighting here the triple bottom line environmental, social, and economic factors that are included in the CLASIC tool. As you can see, again, I'm not going to read through all of those, but you can see things like mental health or thermal comfort on the social side. On the environmental side, things such as carbon sequestration are included. And then you see, for example, under economic, we have avoided water treatment costs. By infiltrating more water, as an example, we have lower amount of water through the sewer systems, particularly in combined sewer systems. That would mean avoided water treatment costs for wastewater treatment facilities. So as I mentioned, these factors then are reconciled in a multi-criteria decision analysis tool that allows for alternative analysis by building different scenarios. And the user can identify or specify weights for an importance of these different factors. So again, as you can see, there are economic, social, and environmental categories. In this case, you see under economic, one can put an overall importance on the economic factors and then individually make them less or more important to rank the social, environmental, and economic factors as it relates to a specific scenario. So you will see this in the live demo, how we use a dashboard type of output to represent and illustrate the multi-criteria decision analysis results. So the tool has been demonstrated via various case studies that are available from the landing page, homepage of the CLASIC tool. These range from evaluating the effectiveness of low-cost, low-maintenance solutions for reducing runoff and flood control, all the way to things such as how trees, for example, influence urban heat mitigation and things like that. So you can see the list of these 10 case studies that we have performed. I will, for the purpose of this demo, go to City of Philadelphia, which in that case, we have looked at the vegetation strategies in stormwater control measures, whether we should add trees or not add trees. If we have vegetation, what are the trade-offs in adding diverse vegetation versus grass and things like that, both in terms of cost, but also, as I mentioned, triple bottom line, social, economic, and environmental factors that are represented in the model. So if you're interested in learning more about how we model hydrology in the model, the hydrologic simulation model that is incorporated in the CLASIC tool is the SWIM model, stormwater management tool, management model developed by EPA. But we have modified the tool to be able to run the model at municipal scales at computationally reasonable time requirements. As most of you are familiar with this, SWIM is mostly applied at catchment or sewershed level, and also it can be computationally expensive. So we have done the innovative or adopted and incorporated innovative approaches to make this a suitable tool for citywide and regional scale capacities. My colleague, Dr. Mohammed or Mashid, who is getting her PhD, has led a lot of studies that demonstrate how the tool performs compared with observed data, as well as the original version of the SWIM model. Recently, we also published the CLASIC tool in environmental modeling and software by describing lifecycle cost components, as well as triple bottom line social, environmental, and economic factors. So you can see the DOI is here for both of these papers if you want to learn more about these tools. So please contact us via AUSI, the One Water Solutions Institute at Colorado State, or directly contact me if you have any questions about the purposes of CLASIC, how it can be used. If you need technical support or have any questions, please let us know. We would be delighted to help you get started using the tools, and we'll provide technical support for those purposes. Okay, so with that, I'm going to stop, see if anybody has any questions before we go to a live demo of the tool to demonstrate how you can set up a project and run the model for anywhere in the United States. In the continental United States, you should be able to run the model. But before that, any questions or comments that you would like to clarify?
You can feel free to raise your hand or throw any questions in the chat as well.
Okay, hearing none, I'll proceed with a live demo. When you when you go to clasicerams.com, which is the link for the tool, you have to first create a login for CLASIC. CLASIC tool is embedded in our cloud services platform that we refer to as ERAMS, Environmental Resource Assessment and Management System. That's our cloud infrastructure with a platform as a service model. You create an account. That user account can be used for all of the tools that we offer for different water sector, for different analytics that address different water sectors or analysis used by water professionals. So once you log in, you will land in on the homepage, which describes the CLASIC tool. Again, I haven't logged in here yet, so I go ahead and log in. I have my credentials. I sign in here. You see that once you log in, these other options on the left dashboard show up. So in addition to the homepage, you can then get started by creating a new project, which I am going to do. Or if you have existing projects, you can choose from them. So I have already demoed many projects for different communities. In this case, I'm showing two of them, one in Philadelphia for Philadelphia Water Department and one in New York City. But again, for the sake of going over the process together, I'll just create a new project. You can search for a location. So again, I'll search for Philadelphia. This will allow me to quickly go to an area of interest. If you have an exact address, obviously you can do that as well. Then I will potentially go to a highly dense area of Philadelphia. So let me maybe go to an area that, again, it's highly urbanized. So let's say I will choose this area here. You can identify your area of interest by uploading a layer or using known boundaries such as census blocks or block groups or watershed boundaries or whatever you want, or you can again draw a polygon. So in this case, I'll go ahead and draw a polygon to show how the tool would, is set up for an easy way of doing this. At the last point, you have to double click to indicate that this is the end of the polygon. So this gives me the boundary of my analysis. Then for subunits, again, you can use different types of subunits. In this, you can use a single subunit for a very quick analysis, or you can, for example, use census blocks or block groups. So I use census block groups. For land use, we use the National Land Cover dataset. You can choose different years that are available from 1985. For soils, we use the Sergo soils from National Resource Conservation Service. And then I give this a name. I'll just give it a name for the date that we have here. And then you create the project. Once you push create project, what the tool does, it goes and fetches all of the data, including, as I mentioned, land use, land cover, soils, and everything else. Subunits are extracted. So you can see here, now I have 1, 2, 3, 4, 5, and 6 subunits in this area. You can look at different properties and conditions for the project. In this case, I'm just right now looking at the percent imperviousness in the area. Okay, so I simply set up my project by defining the boundary, defining the subunits, both of which can be user defined. One of the neat characteristics of the tool is that during the process, you can always modify all factors, including land use, land cover, soils, and all of the other characteristics in the tool. So I proceed with so for display, again, you may look at soil characteristics. In this case, all of the soils are here very poorly drained, or you can look at population by group. So all of these factors or parameters that we obtain from nationally available data sets are available. For precipitation, you have to choose stations in the area that are representative, or you can upload your own data set, particularly for future climate analysis. Obviously, user-specified data are the best way of doing that. In this case, I choose a climate station to represent the data for a base period that would be my baseline. Same thing with evaporation. I choose one of the stations that we have ET estimation. By the way, these data sets, these climate stations are from the EPA's basin tool. Many of you are familiar with the basins technology and databases. We simply use that approach because a lot of groups are familiar with those kind of data sets. So we provide the climate data. Then for our analysis, again, for each of the subunits here, you can see these characteristics are organized. Subunit 5. So you can look at these different subunits and see their area, imperviousness, slope, percent, medium, or high, or whatever urban development categories, and so on. So there are, again, as I mentioned, there are 6 subunits in this case that we are looking at. One of them, I think, is very small, so it's not very easy to see that. With regard to water quality, we use nationally available data sets for concentration of total suspended solids and nutrients, as well as indicators for fecal and bacterial communities. All of these can be modified. So if, for example, a community has better data for water quality, this can be edited by putting these values in the edit mode and changing them and saving them. Again, I'm not going to do that because we are accessing the information from nationally available data sets. And in this case, I do not have a better data sets to use in this case. But again, the point here is that all of these parameters that characterize the physiographic or climatic conditions or water quality and quantity conditions in the catchment can be modified by using this edit button, and then changing things such as, in this case, flow length, infiltration parameters can be changed. Again, infiltration parameters, we obtain this from either Sergo soils or from other nationally available data sets. Technology effluent concentrations are obtained from the BMP, International BMP database. Again, one can change these outputs, and this is essentially the way that scenario planning for water quality is conducted. We simulate hydrology using SWIM, use concentrations of contaminants by subunits, depending on land use characteristics from nationally available data sets. And then we use the International BMP database to characterize the output of, or the effluent concentrations for different constituents, and we handle it that way. Same thing with lifecycle costs. In the lifecycle costs, we have a database of various cost components in the lifecycle costs, but we also allow a regional cost factor. So if some technologies are, or BMPs are more expensive to develop, create, and implement in a region, there's a regional cost factor that can be implemented to indicate that costs in that specific project are higher than national averages that we are using. So this, again, cost factor can be incorporated. All of these, the explanation for all of these elements are available at the fingertip at each place where these factors are introduced. So again, study period can be changed, and discount rates and everything else can be incorporated there. So the project automatically creates a baseline scenario where there is no technology. The baseline scenario, I'll just keep it as it is. I will go ahead and maybe create a scenario for rain garden scenarios. Okay, so you enter the name, hit enter, and then you can see, you can delete the scenario, rename it, or whatever you want to do. Then you click. For every scenario, you can go ahead and change the climate factors. If you want to have adjustments of climate, again, this is the easiest way to incorporate factors that influence climate change. But again, as I mentioned, the most robust and rigorous way of doing that is for every scenario, the user can go ahead and upload a different climate. Again, I will not change the climate. Land use, you can say that, for this specific scenario, the impervious surface percent may go up by some percentages, or maybe instead of 17% low impact or low intensity urban development in subunit 5, for that scenario, we will have more development. This may change from 17% to 5%, and that is added to medium or high or other categories. Okay, so all of these factors can be adjusted in this case, including concentrations of nutrients and other constituents in the system. But again, the most important part is perhaps the technology category. When you go to technology group, in this case, I'm modeling rain gardens. So I may select in this area small rain gardens where the surface area is about 100 square feet. So if you go to medium, you can see that becomes 1,000 square foot. Again, this is not a design tool, so we just want to see how different type of stormwater infrastructure with different sizes can influence the water quality and other factors, stormwater control in general. You define ponding depth, filter media, depth, and then you can include, again, impermeable linear or not, a seepage rate, and you may include an under drain or not. Okay, if you want to consider these factors. I won't do it for the sake of this demo. I'll add diverse vegetation, but you can have it as grass or diverse vegetation. You can include trees. Now, by default, we have some certain number of trees per different sizes of stormwater technologies. But again, if we want to add more trees, we can always go to this technology and add additional trees for that scenario. Okay, so in this case, again, I'll just keep it as the default values. I mentioned that the rain gardens capture impervious surfaces, not surrounding pervious surfaces. Obviously, then we get more impact from implementation. 10% area capture, you can change how much of that impervious area is captured and depth to capture. So I think in Philadelphia, they use 1.5 inches, but different cities have different design criteria for depth of rainfall, the first amount of rainfall that is captured in stormwater systems. Then you can apply this by clicking different subunits and adding the technology to them, or you can apply to all of them. So when I do this, when I click apply, it adds the rain garden with 10% impervious capture and the acres that it captures correspondingly and how many of them. So the tool automatically computes how many of these technologies we need to incorporate and we can incorporate with the number of trees and so on. So you can see the tool has been designed in a way that it's very simple to set up for planning and management purposes. But again, all of this can be adjusted, including, as I mentioned, if one wants to incorporate more trees, we can go and add more trees to the system. There are advanced scenario options where, for example, cost can be edited for all of these components. Everything is adjustable. So if somebody is bidding on a project, or for a project there is more maybe detailed information available, we can do that. Same thing with effluent characteristics. So everything, again, is adjustable. Then we move to the MCDA component. We can change, as we mentioned, the importance of different factors that are incorporated in the MCDA approach. Okay, so we can make these various factors move. Again, I'm not going to change that for demonstration purposes. If the community has specific targets to meet, whether there's a water quality consent that has to be met or other type of rules and regulations, they can be identified here. And eventually, for all of the scenarios that we build, we'll go and run the model. By running the model, there are two things happening. Run the SWIM model and then calculate hydrologic impacts with the concentration of water quality constituents. We get water quality impacts. And then after that, once the hydrologic and water quality characteristics are simulated, we simulate triple bottom line co-benefits. Per scenario, this will take about 20 to 30 seconds. And then, again, the tool finishes the calculations and goes to co-benefit assessments, which is very fast. A quick note here, if you come to this point and the model doesn't converge and gives you an error, typically that error is associated with lack of adequate precipitation and evapotranspiration data from those climate stations that you select in the beginning. And in this case, you see the baseline already completed in about 20 seconds or 25 seconds, and rain gardens will run. So if you get an error there, first of all, you can always contact us to work with you to figure out what is causing the error. But typically, that means the precipitation and climate databases that we are using have some sort of problem, or the record of data is not complete. We are doing a massive set of simulations for the entire country to be able to add additional databases in addition to the basins database that we use. Once the models run and co-benefits are analyzed, you can see that there's an alert for scenario summaries. If you go to scenario summary, you can see what's the percent imperviousness of all of these, how many, this is the scenario characteristics. You can see under the scenario tab. In summary, you can compare, for example, baseline with the rain garden. So you can see the estimated costs of that scenario. Obviously, I didn't add any technology to the baseline, so there is no cost. You can see the MCDA result in a dashboard format. So when you're comparing scenarios, the aggregated MCDA results are reported here. And you can see hydrologic impact. So by adding those rain gardens, 7% increase, approximately 7% increase in evaporation, 17% increase in infiltration, and almost 10% reduction in runoff by adding those rain gardens in that area can be achieved in this case. Then you can get a more detailed breakdown of costs over time and rehabilitation costs, replacement costs, and all of those. And again, as I said, co-benefits that are listed here. So with that, I'm going to stop here. That's the end of my live demo. If you have any comments or questions, please let me know. I would be more than glad to answer. So again, just a last comment, perhaps. You can use this tool for any place in the lower 48 or the continental United States. The databases are available for these areas. And again, as I mentioned, we are adding readily available data for climate change assessment and even land use, land cover, and population growth scenarios that will be available in the tool in the next version. Right now, we are using the basins databases for climate analysis. So with that, questions, comments, or any type of clarification that you need would be welcome to discuss here. And feel free to unmute yourself and ask the question if you would like to just have a conversation.
Yeah, participants can raise their hand and I can go ahead and get you unmuted. We have a universal setting that I can't change, but feel free to raise your hand if you have any questions or throw them in the chat for us. You must have dazzled everybody.
I don't think so. I think everyone is snoozing, or I know James is.
Yeah, it's not fair because he can't actually turn his microphone back on, but I can. Leslie, I'll go ahead and activate your microphone, but if you're not in a place where you can speak yourself, go ahead. I see you typing in the chat, so we'll sit tight, but you should be able to unmute yourself if you want.
Oh, hi. You hear me?
Yes, go ahead.
Oh, it's not like a specific question. I was just gonna say it's a very interesting presentation and I'm totally awake.
Okay. That's very useful. That actually is a good feedback. Awesome. Okay, well, sounds great. Again, as I mentioned, everybody, please contact us. This is my personal contact information. If you need technical assistance, we host, if needed, for particular consultants and consulting firms. If you're interested for hands-on experience with CLASIC, we can set up workshops like that to go over, maybe set up a specific project that you may have in mind. Or if you're using this for academic purposes, you have an area that you want to set up and you need a lot of interactions, we would be more than glad to help you set up your projects and successfully run the model and simulate whether it's land use, land cover change, or population growth, or climate change, or technologies that you want to model. Contact us and we will set up time with you to get started with the CLASIC tool.
I also just threw in our general email address as well as a link to our upcoming webinars that were scheduled out through August, and we'll continue to build that schedule and host a different webinar each month. So hopefully we see you again and you get to learn more about the amazing tools that we offer here at OWSE. Thank you everybody for your time. We'll get this posted to YouTube, so if you need to share it with anyone, you know how to find it.
Thank you, everybody. Have a good night and day.